Hello, welcome to chapter 14. In this chapter we're going to learn about these distributions called chi-square distributions. And what chi-square distributions deal with is situations where our data is categorical rather than just numerical. Also, it helps us deal with data with many groups of data rather than just a single mean. For instance, here's one situation where it has the number of accidents in a particular area. Are these accidents spread evenly throughout the week? So these are days of the week, and we want to see if they're spread evenly. Well, what we could do is we could do a 1 proportion z-test for each of those values. However, this is not efficient. We want a method for solving one-way tables. This is a one-way table that has 7 cells. So one-way table, it's got 7 cells down there. So we use this thing called a Goodnessoffit test. The Goodnessoffit test is used to determine whether a population of a certain hypothesized distribution expressed as proportions of individuals in a population falling in various outcome categories. Suppose that the hypothesized distribution has k outcome categories. To test the hypothesis, so our null hypothesis is that the actual population properties are equal to the hypothesized proportions. First, we need to calculate this chi-squared test statistic. And to do this, what we do is we take the observed count minus our expected count and square it, and divide it all by the expected count. Then x squared has an approximately chi-square distribution with k minus 1 degrees of freedom for a test of the null against the alternative hypothesis. An alternative hypothesis is that at least 2 of the actual population proportions differ from their hypothesized proportions. And the p-value is the probability our chi-squared is greater than x squared. Now our conditions for this are much different than our conditions have been so far. The data has to come from a random sample. And we also have to say that you may use this test with critical values of chi-squared distribution when all individual expected counts are at least 1 and no more than 20% of the expected counts are less than 5. Now that'll make sense once we get into a problem. So first, let's try to figure out what this chi-squared business is all about. So if we look at this, we have 700 total accidents. And this is how they were distributed by the day of the week. If these were distributed equally, we would expect each of these to be 100. Now to find our chi-squared, we take our observed, which is 20, minus our expected, square it, and divide it by our expected. So take a second and do this on your calculator. Alright, the answers that I got were 64, 10.89, 6.76, 34.81, 12.96, 1.69, and 75.69. Now, these values are the highest the further they are away from the expected value. If they're close, like 113, you can see that this value is very small. But if they're further away, like 13, you can see that this value is high. So now what we want to do is we want to sum up all of these values. So we take a sum of them, and I get 206.8. 206.8. All right. Now we'll use that in our, so to find the sum, that's 206.8. Now we'll use that in our write-up. So our null hypothesis is that it doesn't matter which day that you get in accidents, so the accidents are evenly distributed. Accidents are evenly distributed throughout the week. So our alternative hypothesis is talks about how accidents are not evenly distributed throughout the week. Now, this data did come from a normal sample. I didn't tell you about that. I didn't write it out, but the problem I got it from, it said that the data comes from a random sample. Also, we should talk about the other two conditions. Now, let's go back and visit them. So we have to say all individual counts are at least 1. So are all these at least 1? Yep, check. So, and at least, and no more than 20% are less than 5. Are 20% less than 5? Actually, none are less than 5. So both of those conditions, we can say all expected counts are greater than 5. So those are the two conditions, and that's it. You don't have to worry about any other conditions for chi-squared. Now we have to figure out the p-value and then make an interpretation. Now the p-value, there's a couple different ways to do the p-value. Now we got a number, a chi-squared number, and let's look back. Where did we get our chi-squared number? 206.8. So our chi-squared number is 206.8. So now we want to find a p-value based off of that. Now there's two ways we can do it. One way is to go into the back of our book or our formula sheet, and there's a chi-squared distribution table. Another way is to use our chi-squared CDF. So if you use your calculator and hit second distribution, or second vars, chi-squared CDF is right below the TCDF, and it looks like this. So what we'll do is hit chi-squared CDF, 206.8, comma, a very big number, and then we have to hit the degrees of freedom, which is 6. So 206.8, very big number, and then degree of freedom, which is 6. Now this gives us a very, very low number. So our p-value is essentially, or I should put some squiggly lines, essentially 0. I have 6.7 times 10 to the negative 42nd. That's really low. So our interpretation is we reject our null hypothesis because our p-value is so low. So we have evidence that accidents are not distributed evenly. Throughout the week. All right, there's our write-up. Now the chi-square distribution, it's a little bit different than our other distributions. If I had just had a degree of freedom of 1, it just looks like this, which is a pretty crazy graph. A degree of freedom 4, it goes up and then comes back down, and it's really skewed to the right. Even degree of freedom of 8, you can see it's looking more and more bell-shaped, but it's still skewed to the right. All right, here's another example for biology example. Red-eyed fruit flies. Biologists wish to mate 2 fruit flies having genetic makeup of R, big R, big C, little c, indicating that each one has 1 dominant gene and 1 recessive gene for eye color, along with 1 dominant gene and 1 recessive gene for wing type. Each offspring will receive 1 gene from each of the 2 traits from each parent. The following table is often called a Punnett table and shows possible combinations of genes received by the offspring. So here it is. So to sum it up, any offspring that receives the big R gene will have red eyes. So all these big R ones are going to have red eyes. Any offspring receiving a C gene will have straight wings. So based on the Punnett table, the biologists predict the ratio of 9 red-eyed straight-winged, and then 3 red-eyed curly-winged, and 3 white-eyed straight-winged. And then finally, there'll be 1 white-eyed curly-winged offspring. To test this hypothesis about the distribution of the offspring, the biologists mate the fruit flies. Of 200 offspring, 99 had red eyes and straight wings, 42 had red eyes, curly wings, 9 had white eyes, straight wings, and 10 had white eyes, curly wings. Does that data vary significantly from what the biologists had expected? So let's set up a hypothesis test. Our null hypothesis is that that the ratio would be 9 to 3 to 3 to 1. So 9 to 3, so there's a ratio. There's a ratio of 9 red-eyed straight winged to 3 red-eyed curly wing to 3 white-eyed straight wing, and then 1 white-eyed curly wing. All right, the alternative hypothesis is that at least one of these is true. All right, so let's check the conditions. It doesn't say whether they have, didn't say about a random sample. So, doesn't talk about random, say, random sample. And let's look at the expected counts. So if there's 200, it would be 9 to 1, 9 to 3 to 3 to 1. So 9 plus 3 plus 3 plus 1. That would be 16 total. So we would expect 1/16 of them to be wide-eyed and curly-winged. And if I multiply 1/16 times 200, My smallest expected value will be 12.5. So we'll just say all expected counts are greater than 5. Alright, so now let's look at the calculations. So let's say red eye curly. Let's just shorten this. Say not curly, red straight. The observed is 99. The expected, maybe I'll put a little O and a little E here. It's 99. The expected, well, we'd have 9/16 of them, or 0.5625. And if I multiplied that by 200, my expected is 112.5. Now, if I have red curly, now my observed was 42, and my expected, that would be 3/16 times 200. That's 37.5 would be my expected. Now 49 are white-eyed and straight. And so if that's 49, my expected count again is, since it's the same proportion as this, it would be 37.5. And then white pearly, we already figured this out. I forgot what my answer was. 1/16 times 200, 12.5. And I forgot what we got. 10. Alright, now you can see this data doesn't hit perfectly. So let's see what our chi-square distribution is going to look like. We take O minus E squared, and let's take a look. Alright, I did these on my calculator, and I got 1. So it's observed minus expected squared over expected. I got 1.62, 0.54, 3.53, and 0.5. Now we have to add these up, and I get 6.19 as the value. So 6.19, we want to find the probability of that. So to get our p-value, we can use our charts, or we can use the chi-square CDF. So we're going to go from 6.19 to a very, very big number. And our degree of freedom here, since there's 4 items, will be 3. So chi-square CDF 6.19, comma 99999, comma 3 will give us a p-value of 0.1027. Alright, so now let's interpret this. Since the p-value is higher than 0.05, we fail to reject the null. So we don't have evidence that this group of fireflies, not fireflies, they're fruit flies, differs from their proportion. All right, those are two chi-square tests we did today. Hopefully that's good enough to get you through the homework.